Hi everyone, Chris Tisdell here again. Thanks for tuning in. In this video, I wanted to share with you some new mathematical research of mine, and it kind of bridges between mathematics and teaching and learning. So I think this video will be interesting for people who learn and teach mathematics or who just love mathematics. Okay, so the content is based on a new research paper. I've put the link to the paper in the description, so I hope you enjoy that. And essentially, it involves second order differential equations. Okay, and very basic second order differential equations, ordinary differential equations. And what I've tried to do here is to rethink how we learn and teach the subject of second order differential equations. Okay, so pedagogy just means learning and teaching. And in particular, I'm going to look at well-posed problems. So when does a solution exist and is it unique? Now, I won't talk about all of that in this paper, but in this video, but you can go and see it if you need some more information in the full paper. Okay, so I'll talk about the abstract, introduction, and talk about the approach and the main result. All right, so why is this interesting? Well, I'm glad you asked. Okay, so firstly, knowing an equation has a unique solution is important from both a modeling and a theoretical point of view. So if you see some sort of dynamic phenomena and you want to model it, well, the equations that you come up with aren't very good if there's no solution or multiple solutions. Okay, so one of the basic questions we ask is, does a given problem, or perhaps related to a model, have a solution or not? Okay. Now, for over 70 years, the approach to learning and teaching of this well-posedness of initial value problems for second and higher order differential equations has involved a simple technique where we transform the problem to a first order system. And this is a very well-known technique. And if you look at all the textbooks over the last 70 years, you'll see this technique over and over and over again. Okay, so what I'm looking at in this presentation is that it's the transformation to first order systems is interesting, but it's not necessary. Okay, so I'm going to say that this is not necessary, and I'm going to present a more direct approach. And in particular, my ideas do not require an understanding of systems of equations. Hello, Matt, just looking at the live chat now. Okay, so what I'm trying to do here is look at long-held techniques and try to propose some other techniques that don't need an understanding of systems. Okay, so here is the problem under consideration. You've got a second order ordinary differential equation. It could be linear, it could be non-linear. And you've got some initial conditions. So tau is just a point, a and b are constants, and f is some appropriate function. Now, in early mathematics courses, you will see these kinds of equations all the time. So in high school, in university, you would see them when you look at vibrating systems, when you look at the falling of bodies under gravity, electrical circuits, and the motion of a pendulum. So you could even argue that these kinds of equations are even more important than first order equations. Okay, a little bit controversial there, but some people think that these are so important. The second ones are even more important than first order problems. Okay, so we're going to look at this problem and we're going to ask ourselves, when does this problem have one and only one solution? Okay. All right. Now, I think I said this before, but let me just remind you. The question involving whether or not a differential equation is well posed is a really important one. And in fact, if you look at some of the classic textbooks, this one's by Agnew, Agnew thinks they're so important that he states in the book, a student of differential equations should know these theorems on well-posedness as she knows her multiplication table. That's how important these well-posed problems and theorems are. Okay? So when we say well-posed again, we're talking about, does the problem have a solution and only one solution? All right. So what do we do then? What is the method that we use? Well, like I said, we stay away from first order systems and we're going to directly deal with the second order problem and its integral equation. Okay, so underneath this is a way of measuring distance between functions. Okay, and the way that we measure it involves the well-known exponential function. Okay, and I'll show you that in a minute. All right, so let's say we get these results. Well, how are they useful? Well, from a learning and teaching point of view, from a pedagogy point of view, students and teachers now have some more tools, a different perspective on an old question. Okay, they no longer have to go to systems of equations to solve this problem. They can just do it directly. And I might also need to say that our ideas extend to nth order problems. We've just looked at second order problems, but nth order problems are achievable too. All right, so here is the main result that I'm going to show you. Okay, just squeeze it in there. Okay, so we're assuming that f's continuous and you've got some sort of three-dimensional infinite block there. We assume this inequality down here of f on S. So for all points or pairs of points in S, this inequality holds for some constants L and M. This is traditionally known as a Lipschitz condition. For second order problems. Okay, now it looks a bit crazy there, but there are very simple sufficient conditions that will guarantee three holds. Okay, so under those conditions, the conclusion is the initial value problem 1, 2 has at most one solution on an interval like this. Okay, and tau's a point in between A and B. Now, I'm not going to talk about the existence part of that. I'm going to talk about the uniqueness. So at most, so we say that essentially what we're really restricting our attention to here is that there's either one solution or no solutions. All right. All right, so continuity plus Lipschitz gives us what we want. All right, so how do we do it? Well, I said before that we look at a direct approach. Okay, so this is an example of an integral equation. Here's f, here's b, here's a, tau, etc. And this is the equation that we're going to look at. We're not going to move to a system. All right. So first of all, what we do is, instead of moving to a system of problems, we transform this original problem to an equivalent integral equation. So basically, x solves 1, 2 if and only if x solves 4, and we go to work on this. Now, earlier on, I talked about using a new distance function. Well, we're going to measure the distance between a function x and a function y through this D1 metric here. Okay, you can see we look at the absolute value of the difference between the functions and their derivatives, and we divide by this exponential function. Now, beta is just some constant that we'll choose a little later. It'll be for convenience what we do later. Okay, so we haven't fixed that yet. Okay, now D1, like any good metric, satisfies the following condition. It's 0 if and only if the two functions are identical. And that's going to form part of our major proof here. Okay, so let's get into it. What we're going to do is do the classic case where you go, okay, well, let's assume that two solutions exist. We'll end up with showing that the two solutions are identical. They're one and the same. Okay, so assume there's two solutions, x and y. We show that x and y are identically equal. How do we do that? Well, we're going to use the assumptions of our theorem and our D1 metric. All right. So let's start. Okay, so if x and y are solutions and they both satisfy 4, so you can take one away from the other and divide by this exponential and you'll get something like this, okay? So these bits cancel out, but you'll be left with this bit for x and this bit for y. So you just take the difference, okay? All right, so now what? Well, we're going to now apply our Lipschitz condition 3 to this, okay? So let's see if we can do that successfully. So applying the Lipschitz condition, we end up with this. So we get a bit of a mess here now, okay? And this is starting to look a bit like this now, the D1 metric, okay? So what I've done now is I've inserted, been a bit sneaky here, I've inserted an exponential up here and down here. So we're essentially multiplying by a factor of 1 there, okay? So now what you can do is you can play with the exponentials and come up with this. You can take the maximum of these two things and move them out the front. So now you can see this is very much starting to look like the D1 metric. And what is this? Well, we can simplify this, and I've simplified it in the paper. This is actually less than or equal to 1 on beta squared. So you get this big thing here times 1 on beta squared, okay? All right, and so here it is. I know the font's a little bit smaller on this page. So you get down to this. So take the maximum of L and M and you get this. So I've now got an inequality involving this in terms of beta, L, M, and the D1 metric. Okay. All right, so what next? Well, let's do the same thing where we have primes here, x prime and y prime. Okay. So similarly to the above, you look at this, you won't have essentially you can get this just by differentiating this. So this essentially disappears when you take one away from the other. This little kernel bit disappears and you get that minus that. Same sort of idea, apply the Lipschitz condition, multiply through by a factor of 1 involving the exponential functions. And we get a similar setup to what we have down here. Okay, now this is just less than or equal to 1 on beta. Okay, so let me see if I can get that in the right spot. Yeah, so now we have something similar, an inequality involving these primes involving L, M, beta, and D1. Okay, so let's add what we've just come up with. We're going to add this to this, and the right-hand sides will be added together, and you'll continue the inequality. Okay, so if I clean that up a bit, and this is what I get. Okay, so I've added basically these two things and taken the maximum. of them and continue the inequality. So that's where the D1 comes from on the left. Now let's rearrange. We've got D1 there, D1 there. Let's rearrange them. We get this big mess here. So this left-hand side is less than or equal to 0. But this is certainly greater than or equal to 0. So we can force D1 to be less than or equal to 0 just by making this assumption here. Now remember, we don't know what beta is, but we can choose it as large as we like. So when beta is large, this will be small, okay? This will be small because 1 plus beta plus 1 on beta squared will be small. So this definitely can be less than 1. Doesn't matter how big L and M are, I can always choose a beta large enough so that this will be less than 1. So what does that mean? Well, this big bracket here is positive. Okay, so that's positive. That's greater than or equal to 0. But from 5, we see the metric is less than or equal to 0. So what that means is that D1 equals 0. So X and Y are the same. Okay. Now this just comes back to one of our assumptions over here, that D1 is 0 if and only if X equals 0, right? That's one of the properties. Okay, we've just shown that D1 equals 0. So we conclude that X and Y are one and the same. So we've set out what we chose to show. We tried to show that X and Y were the same. Okay, there's two solutions, but they're identical. Okay, so that's it. That's pretty much the uniqueness part of the proof. Okay, now I won't go into the existence part. You can see that in the paper. The existence part is very well known anyway, but here are a couple of references. Here's Agnew's book, which is a complete classic, where I got that great quote about well-posedness theorems and multiplication tables. Hope you like that. And this one is the brand new paper that has just been published today, and I'll put a link in the description for that. Okay, guys, thanks for tuning in. Hope you're having a great day. If you have any comments, any questions, happy to answer them in the comments section. And thanks for watching. Okay, bye everyone.